Very good. So let us continue with our explorations. We were trying to understand how to study scattering amplitude. So we have a given scattering amplitude or a partial scattering amplitude with momentum k1, k2, k3, and so on. And as we said, this object is equal to the expectation value of a Wilson loop, where we concatenate one after the other this vector. So we put k1, after k1 we put k2, after k2 we put k3. And you see I drew an hexagon because here I drew a 6-point amplitude. And if the momenta add up to 0, this is a closed polygon. Okay? And our goal is to study this object, this Wilson loop, which is a Wilson loop that depends on the 't Hooft coupling of the gauge theory and on the geometry of the polygon. Okay? And of course, this, I should say that this is properly better understood after proper regularization to get rid of the UV divergences of the Wilson loop, that is to say, of the infrared divergences of the scattering amplitude. Okay? So we will go one step by step. So first we will start with reviewing a little bit or explaining a little bit some things about the geometry of null polygons. Next we will address this small issue of how to properly regularize such that we are not discussing that 0 is equal to 0, but rather some proper physical quantity. And then tomorrow we will start going into our explorations of more dynamical stuff and understanding how do we go up in the coupling, down in the coupling, and how do we move non-perturbatively in these objects. And that's where integrability will kick in. Okay, very good. So we start with a polygon, okay? And we have a point, a cusp of the polygon, which is some point x mu in Minkowski space. Okay? Very good. So this is a cusp of my polygon. And now we want to find some good observables for describing these null polygons in a conformal field theory. So some good variables where conformal transformations act naturally. Because, for example, we know that this x mu is a bit terrible once we will start considering special conformal transformations. We get these disgusting z squares and so on, something very nonlinear and not so nice to deal with. So the first thing that we can do following João is introducing this light-like variable P, A, which is now a light ray in R2,4. We are doing Lorentzian. So this light ray, I can always write it. So light rays are projective, so P is identified with lambda P. So I can always write it as some lambda. And then I can write 1 x square x mu. Here I'm using slightly different notation from João. These are light cone directions. So if you take the average, 1 plus x squared over 2, 1 minus x squared over 2 were what he was using in his lectures. And this x mu is just this point here in Minkowski space. So this is a null vector. I mean, the norm is just this times this minus this square, so it is 0. And the idea is that this, a light ray in R2,4 is equivalent to a point in Minkowski space. Right? And what is nice is that conformal transformations act linearly on these vectors as Lorentz transformations. So Lorentz transformations are just equivalent to conformal transformations. Okay? So for example, if we act with a transformation of SO2,4 that just rotates these components here, then it's obvious. It's the same thing as in the 4-dimensional space. But we can act with some conformal transformations that rotate some components here into some components here of the light cone. Right? I can take a bit of x squared and put it here, or a bit of x squared and put it in the one slot. Then when I shift lambda such that I go to this section, to this so-called Poincare section, I have to rescale to absorb those rotations, and that's what leads to the nonlinear transformations for x mu. So they are inherited once I act linearly and then rescale to go back to this representative. So it's a very useful notation. Okay. We want, however, to go one step further and think of this vector, PA, which is a vector of SO6 roughly, okay, 2 plus 4 is 6, okay, so of SO2 comma 4 as a bi-twister of SL4, which is equivalent to which SO2 comma 4 is basically SL4. So what we are going to do is very similar to what Freddy was doing for spinorilicity. So we take our null vector, now it's a null vector in 6 dimensions, not in 4 dimensions, and we contract it with the analog of Pauli matrices, but now these are matrices that are 4 by 4 matrices. So these are the 6-dimensional sigma matrices. So these are the R2, 4 sigma matrices. In the same way that the usual Pauli matrices that Freddy was using are the R1, through sigma matrices. And in the same way that the gamma matrices that Carlos was using are the R1, 9 sigma matrices. Okay? So just exactly the same thing. And now something special happens, like for Freddy. So for Freddy, when Freddy was contracting a P mu with a sigma mu, it was a product of a spinor and in the fundamental and one in the anti-fundamental. Here, because this P is null, it turns out that we can write it as a product of two twisters, ZA and WB, antisymmetrized. Okay, these matrices are antisymmetric. Okay, so this A here runs from 1 to 4. These are called twisters. Okay? Very good. And there is a fancier notation for this, which is to indicate the point P. We can write it as a wedge product Z wedge W. And this wedge product, what's important to keep in mind about this notation that is emphasized here is that this product is antisymmetric. Okay, so it's a kind of scalar product, but that's antisymmetric. So Z wedge Z is 0. Very good. So it will be clear in half a second why this is a slight improvement over using this excess. So let me just say that in the same way that conformal transformations act linearly on this piece, they also act linearly as SL4 transformations on this Z and W. Okay? Like the Lorentz transformations, they act linearly on P mu, and they also act linearly on lambda and lambda tilde that Freddy was introducing. Okay? So far, from the point of view of acting linearly, it's not yet obvious why we gained so much, but it will become clear now why this is some improvement. Because it will trivialize the fact that all these distances are null. So to see this, it's useful to think what is xi minus xj square. If we have 2 points where this point is associated to a twister z and w, and the other point to a twister z tilde w tilde. Then, well, the only thing that you can form out of this twister that is SL4 invariant is the determinant of the matrix built out of them. Okay? Of course, this quantity is not SL4 invariant. It's a distance. It's not invariant under conformal transformation, so it's natural that what we are going to write here is a bit ugly, but it will soon drop out. We have to go to this representative where we have 1 in the first component of my vector P, that 1 there. So that amounts to dividing here by some z dot the plus component of these sigma matrices dot w times a similar factor for the tilde part. Okay? So these factors are totally irrelevant, as we will see soon when we'll construct proper quantities that are conformal invariant, but if you want the correct relations, this is what it is. So again, this bracket, when we have this bracket here, this bracket is nothing but the determinant of the matrix built out of these twisters. So it's a 4 by 4 matrix. In other words, it is just epsilon A, B, C, D, Z, A, W, B, Z tilde C, W tilde D. Okay? So it is just an SL4 invariant. SL4 transformations have unit determinant. So if you apply an SL4 transformation to each of the vectors, you just get out some power of the determinant, which is 1. On this combination, as soon as we form cross ratios, which are better quantities, xi minus xj square times xk minus xl square over, say, xi minus xk square xj minus xl square. Okay. Then something nice happens, which is that these factors here drop out. And indeed, we have a conformal invariant quantity given by a ratio of SL4 invariant brackets and nothing else. So we get just the bracket, for example, for x, let me use the notation zi, wi to indicate the twistors of xi. For xj, I use zj and wj. And then you can figure out, you write the other brackets, and all these factors there drop out. Okay? So writing conformal invariant quantities in this language consists of writing ratios of these determinants. But this is also not an advantage. I mean, of course, in the embedding, it was also very simple. It was just scalar product of these light-like vectors, right? It was just xi dot xj and so on. So this is just some simple statements about kinematics. And but now we can see immediately how we can make a distance 0. So let me write a solution right away for the polygon. Suppose I have a polygon. Okay? And I want to parameterize these points in a way that they are automatically all null. So what I will do is I will take a point, and I will say this point is made out of two twistors, right? Each point is a product of two twistors. Let this point be a product of z1 and z2. And let this point be a product of z2 and z3. That is, I associate a twister to each edge of my polygon. Z4, in this case Z5, and Z6. Okay? Because if I do this, then you see what happens. When I have xi minus xi plus 1 square, this is proportional to a determinant where I have zi plus 1, and then zi plus 1, zi plus 2. But it's a determinant where two columns are the same, so this is immediately 0. Right? I just have epsilon dotted with two vectors that are the same. So this is automatically 0. Okay? So if we make a small table, we would say, let's see, what did we gain? So we have x mu, we have this PA, and we have this ZA. So concerning the action of the conformal group, this one is complicated, this one is good, and this one is good. Right? Concerning the fact that the points are automatically null and that we trivialize the geometry, this one is not so good, this one is still a bit complicated, and this one is perfect in all aspects. Right? We just trivialize everything that we could trivialize. Now, if you want to generate null polygons, all you do is you give me some random set of four vectors, of four twistors. So you can just really generate random vectors, z1, z2, z3, up to z6. Whatever vectors you give me, automatically we get a null polygon. Okay? You can freely change each of them and so on as if they are totally unconstrained variables, and they automatically generate null polygons. Yes? Yeah, this is what's here. LC, light cone directions. Sigma plus is basically what makes sure that when I construct my P, then I divide by the first light cone component to make sure that I put it to 1. I could also think of it as the infinite twister, yeah. Yeah, that's true. There is a way of thinking it. So the point is that this distance here, there is an arbitrariness in defining what this is. Because I can always do conformal transformation and change it. So I pick some reference frame, and I do it once there, and then I keep that frame. Now, I don't want to discuss frames and changing frames and so on. So as soon as possible, I try to go as fast as possible to conformal invariant quantities where these things drop out, and I don't discuss this anymore if I'm dealing with a CFT. So this is an intermediate step. Just if you want to really have distances, for example, you might want to check if some polygon, if it's globally space-like or time-like or something. And if you really want to set some frame and make sure that you are in a region where things are Euclidean or whatever, you might want to do it. But for most practical purposes, what you want is cross ratios. And for those, all these things drop out. They just transform under SL4 transformations, 4x4 transformations of unit vectors. So this nice here, so this is nonlinear. This is just Lorentz transformations, right? 6-dimensional Lorentz transformation, and here 4 dimensions SL4. Become just SL4, okay? So these guys are twistors which are acted upon by just SL4 transformations. Just that. Okay, very good. Perhaps it's not, but it's true. Yeah. Yeah, it's possible to find yeah, it is true. One way of yeah, it's true. I don't want to explain why, but if you want to ask me in the break why. Because another way of getting to these twistors, for example, if we start with this spinor helicity that Freddy was saying, then you do construct this explicitly. So that's a constructive way. The way I'm doing it is going from the embedding direction. So we meet in the middle, but it's possible to continue a bit further and reach eventually the spinor helicity formulas, for example. Okay, so now a few comments. So what is, for example, the number of cross ratios for a polygon of a given n? For example, for an hexagon. Well, how is it? So to parameterize a polygon, we need to specify n twistors, right? So what's the most naive counting of all, if we really don't think much? Well, each twister has 4 components for n. Right? So that's the most basic counting of all. Now that's wrong, of course, because these twistors are projective. So of course they don't have 4 components. So something a bit less naive would be to say 3n, where 3 because they are projective. So you can always put one of the components, set them to 1. But that's still not okay, because if I pick a particular twistors, I can act on all of them by SL4 transformations. That is a group with 15 elements. So basically I have to subtract those 15 elements. Okay? So this is it. So you see that for 4 points and for 5 points, there are no cross ratios. So they are the analog in a correlation function in the CFT setup of the 2 and 3 point functions that we were hearing, which are points which don't have cross ratios. Whereas the hexagon, which is 6 points, is the first example. You see, the hexagon has 3 cross ratios, would be the analog of the 4-point function here. The first case that has some non-trivial dependence on the geometry. Okay? Very good. And we will see this very explicitly, this analogy between these objects and the 2 and 3-point function of a CFT. We will see them really in great detail. Let me maybe just make one detail, since Freddy was explaining this PCFW, but I hope I'm not saying something wrong. It's not something that I know very well, but I just wanted to say because I think it's correct. But it's good if Freddy checks that I'm not saying something wrong. So suppose I want to also do some kind of BCFW deformation and consider some deformation that changes these vectors, changes just to show you how simple it is. Suppose I want to change these 2 vectors, like Freddy was changing K1 and Kn. This will be K1 and K6, right? I change these 2 vectors, keeping the other ones fixed and preserving momentum conservation, right? So in other words, what I want to do, if I want to do BCFW, is take this cusp and move it with some 1 parameter family Z, right? So this will be doing some kind of BCFW deformation, right? I take this point and move it. This changes this vector and this vector, keeping the polygon closed, which is keeping momentum conservation, and keeping these edges null, right? This was not very hard, but you had to think a little bit. Freddy was choosing this sign plus Z, minus Z, making sure the signs were correct, and so on. How could you do it here very simply? You could say that Z1, let me parameterize it, and go to a deformed Z1, which would be Z1 plus this complex number Z times Z2. Because you see, if you change Z1 by a bit of Z2, okay, what happens to this cusp? Does it move? No, why doesn't it move? Because what is this point here? Remember, this point is Z1 wedge Z2, which is antisymmetric. So if I add to Z1 a bit of Z2, this point is not moving. But this one is, because now this point here, that was Z6 wedge Z1, is moving a little bit. So I'm just moving this point here and nothing else. Okay? So it's an even simpler deformation, you see? It's a deformation of the external data where you touch only one twister. It's a very elegant deformation. You are allowed to change just one twister. Very good. So now let's start exploring a little bit more these polygons and trying to take some juice out of them in the same way that Freddy was building on these three-point structures. For us here, the fundamental objects will be these squares and these pentagons, so I want to spend some time with them. So let's start with squares. Okay? Well, let's start with squares. So squares, all squares. So let's, for example, ask one question. What are the symmetries of an all square? Okay? So we said that the conformal group has many generators, 15 generators, right? Many generators. Now I put a square, so I break some symmetries, right? I put the square. What are the remaining symmetries? And let me show you how, using these twisters, we can get to the answer without thinking, and then let's think why indeed this answer is correct. But it's good that we have a formula which is powerful, that we can get to answers without thinking much. So we have a square, and now we have 4 twisters, therefore a twister Z for the top, Z for the right, Z for the bottom, and Z for the left. Okay? And by an SL4 transformation, because I can always apply an SL4 transformation, and this is a conformal transformation, I can always diagonalize them and write that the top twister is the twister with a 1 at the end, the bottom twister would be the one with a 1 in the next to the last, say the right twister would be the one with a 1 in the first slot, and the left twister would be the one with a 1 in the second slot. Okay? I can always map it to this by a conformal transformation. You see, now that I map to this, there are no parameters parameterizing my square. It is just a bunch of 1s and 0s, which is consistent. We said that squares have no geometry. There's no cross ratios. So there are no families of squares. There's a square and that's it. So it's good that I just mapped it to something and I can. So what are the symmetries? What are the SL4 transformations? So I want an element M, which is an element of SL4, that I want to preserve, that I want to act on these twisters and leave the twisters invariant. Or invariant up to rescaling, because Z is equivalent to lambda Z, right? All these are light rays and so on. They're all projective. So what can I do to preserve a diagonal matrix? I can act with the Cartan generators of SL4. So a diagonal transformation will leave these twisters invariant. Okay? So let me write the most general diagonal transformation. There are 3 Cartans, so there are 3 parameters. Let me write them like this. E to the sigma minus I phi over 2. E to the minus sigma minus I phi over 2. E to the tau plus I phi over 2, e to the minus tau minus I phi over 2. So this is just the most general parameterization using the 3 generators of the Cartan. It's a diagonal transformation, and when it acts on each of these twisters, just multiplies them by a diagonal factor, and therefore it is just the same twister, just rescaled. And this has unit determinant. Okay? If it doesn't, I made a typo, which is possible. For example, here is one. Okay, very good. Do you agree? So the square has 3 symmetries, M of sigma, tau, and phi. So these are the symmetries of a null square. So now let's give them some simple geometrical meaning. And for that, it's helpful to do the following exercise. Let's take our square. Let's take our square. Put a point here and see how this point moves when I act with this symmetry on it. So what is this point? So this point here is a linear combination of this point and this point, right? So it's a linear combination of z left wedge z bottom plus some parameter, it's a linear combination, plus S times Z right wedge Z bottom. Do you agree? Just a linear combination of those two cusps. And now, when I act with M, what happens when I act with M? So let's see. So Z bottom appears here in both cases, and Z bottom as 0, 0, 1. So it is just rescaled. There is an overall rescaling. Let me take it out. By e to the I phi over 2 plus tau. Okay, that's just this third element of this matrix here. Okay, so this is what happens to Z bottom. And then what happens to this Z left? Z left is 0, 1, 0, 0. So it gets shifted by e to the minus sigma times Z left wedge Z bottom. You say that there's also a phi stuff, but it's common to both. I'm also going to take it out in a minute, so wait a second. And Z right is shifted by e to the plus sigma times Z right wedge Z bottom. And as we said, there is some phi factor that comes out that just removes this over 2, right? Or maybe cancels the phi completely, I don't remember. But it doesn't matter because it's an overall factor, but let's see. So left and right are in the first part. Yeah, they just cancel the phi dependence. Ah, thank you. Thanks. Times ds. Good? Do you agree? So this effect, again, up to a rescaling, this is equivalent to saying that S goes to e to the 2 sigma times S. Right? Again, only the overall, the relative coefficient matters. Do you agree? So what is this sigma doing? Sigma is taking a point here and moving the point in this line. That's what sigma does. Sigma moves points. Sigma going to minus infinity means the point going to the left. Sigma going to plus infinity means the point going to the right. Is it clear? So similarly, you can do for tau. So what you conclude in the end is that this tau and sigma have a clear interpretation. Sigma means translations here, and tau means translations here. So this sigma translates points from here to here. This would be sigma equal minus infinity. This would be sigma equal plus infinity. Similarly for tau. And phi doesn't do anything at all. You see? Phi doesn't act on the points. If you act on a point here or on a point there, phi doesn't act. So how do I think? I think that this no square, I can draw it, say, on this plane. And there are two more directions that are orthogonal. So there are an SO2, a U1 of rotations in the two orthogonal directions. That's the phi. The phi is rotations in the orthogonal plane. It just doesn't touch the square. Okay? So you see, we reach this conclusion without thinking too much, just following our nose and seeing what the algebra is telling us. But now let's do it thinking a little bit, so that the conclusion will be the same. So now we start thinking, we start from here and we go there. So let's start thinking. So the idea, as we said, so we take any square. Okay, so this is an all square. And by a conformal transformation, all squares are equivalent, so I can put it in a plane where this direction is some null direction x plus, and this is some null direction x minus. Okay, so all squares, I map and I put it in the plane. For example, I can choose this to be 0, this to be infinity, and I can choose this to be 0 and this to be infinity. I can further, once it's in the plane, apply some transformation that puts this point at 0, infinity. Now, what is the generator now? What is this generator here? This generator is just x plus d dx plus. Just dilatations that preserve 0 and infinity. This is what is the generator d tau. Similarly for d sigma. And now it's clear. This is in the plane, and there are the two directions outside the plane. This is the angle phi. Okay. But if I would explain in this way, you might ask me, can I really put all the squares in the plane? Is it really true? And so on. You'd start asking me all these annoying questions that the way I did it, you cannot. So this is the power of these twisters. Very good. So any question here? So again, what we said is that the square has no cross ratios. It has three symmetries that have interpretations of translations in space, in time, and rotations in the orthogonal plane to the square. So having done squares, we go to pentagons now. So let's take a pentagon now. Where we have bottom, left, top, right bottom, and right top. Yep, just the way I'm choosing to label it. So again, we have the freedom of fixing these twistors as we want. There are no cross ratios. We should not choose them to be degenerate, but otherwise we are free to choose, for example, this bottom to be 0, 0, 1, 0. This right bottom to be 1, 0, 0, 0. This left to be 0, 1, 0, 0. This right top, let me choose it to be minus 1, 0, 0, 1. And this top to be 0, 1, minus 1, 1. Okay? Just my choice. Yes?
Why could you choose it like this and also
Why could I...
yeah, I mean, you need to do the counting.
I could do an SL4 transformation to fix some twistors, and then once I apply the symmetry, so let me see what's the best way to say. So first there are no cross ratios, right? So we know these guys have no cross ratios. So there's nothing very important in what is the precise value of these twistors before I start considering conformal invariant quantities. But another thing is that I can in fact consider most general twistors and then start applying to them symmetries of some squares that I will draw in a minute, and this allows me to rescale a couple of elements and bring the twistors to this form. But this you will have to wait a little bit to see. So perhaps ask me in 2 minutes. For now, it's just my choice of twistors. Knowing that a pentagon doesn't have cross ratios, I choose these twistors. But if you want, don't put precise values. I want to put precise values because soon I will tell you to do an exercise that will involve precise values. But if you forget about these precise values, I just have 5 twistors. Okay? I think for the argument we don't need these precise values. Okay? Now, let's suppose we want to do the following exercise, which is a nice exercise that shows you again how these twistors are nice to deal with null geometry. Suppose I want to find a null line that starts from this cusp and intersects this line. And I want to find this point. Okay, my question is, where is this point? This line is null. Okay? So suppose I want to find this question. So first note something, that this line does something fun. It splits the pentagon into 2 objects, right? If this line exists. It splits into a pentagon in a region that we can call bottom square. Let me call it square B, and top square. You agree? So now let's find what this point is. So what is this point here? Well, this point here, P, let's use Joan's notation for this point, P. What do we know about it? Well, we know that this point here, is given if I specify a twister Z to this middle line. Right? If I specify a twister to this middle line, then I take this twister with this twister and I get this point, this twister with this line and I get this point. Right? So finding this point is equivalent to finding what could be this middle twister. Now, what do we know about this middle twister? Let me write a couple of things. For example, we know that this middle twister wedge the right top is the same as the right bottom wedge with the right top. Right? Because this cusp can be either thought as coming from these two twisters or these two twisters. Both twisters intersect at the same point. Right? So what does it tell you about this Z middle? So this is equal to this. What does it tell you about Z middle? Sorry? So of course there is a naive answer. The naive answer that is someone should say it, just so that we can advance. So, right bottom. But this is naive because there's something more we can do. Plus something proportional to RT because it's antisymmetric, right? And we can put some coefficient beta. We can put in both, but only the normalization, only the relative coefficient matters, so we can put just for one. So our problem, you see, reduces to finding what this beta is. So we just have to find a number, and we found this point, which otherwise would be a nasty problem, finding some conditions, this is null from that, and so on. So we have to find this beta. Now we go to the other side. We go to this side here. And what do we know from the other side? From the other side, we know that this point here is a linear combination of this cusp and this cusp, because it's in this line. So we also know that Z middle wedge Z left is equal to a linear combination of Z top wedge Z left plus Z bottom wedge Z left. So what does it imply now? It implies that Z middle is a linear combination of Z top, Z bottom, and Z left, because again it's antisymmetric, so if I add a bit of Z left I don't see it. Now I'm not even giving names to these guys, because all I'm going to do now is use, if this is true, then the determinant where I put Z middle here and then I put the other guys here, top, bottom, and left, is equal to 0, because the first column is a linear combination of the other three. So now I use this condition where I plug that relation there, and this fixes beta, right? I just put here the Z middle there. The conclusion is that this Z middle is equal to, I just put and I get the ratio of two guys, so let's see, beta, let me try to do it and then we see if it's correct. Z right top, Z top, Z bottom, Z left, Z right bottom minus right bottom exchanged with right top. This is correct. Okay? I just multiplied everything. I mean, instead of putting beta to be a ratio, I rescale everything and make this form. Okay? Is it clear? So now, for example, you can go and see that with this choice of twisters, that's why I was choosing them, but it's not really important, as you see, for this argument. With this choice of twisters, if you compute this set middle is just 0, 0, 0, 1. So this now, I leave it as an exercise. So now, with this exercise, you see what's happening here. What's happening here is that the bottom square has the same twisters as the square that we had before. That's why I chose these twisters outside, because I wanted the bottom square to be the same square as before. I wanted to think as this polygon as I started a square and I put another square on top. So that was just why we chose these twisters, nothing deeper than that. Now I could have said differently. I could have said I specify this square first and then I add these extra lines, but then I connect with the symmetries of this square to rescale a bit the elements of this line and make it a bit more general. But in any way, there's no particular content in the twisters associated to this. Okay, so what I want to point out here is that once you have a polygon and you start asking questions about which point, where is this point null separated from in this line, when are these points null separated, as you see with these two examples that we did, dealing with geometry of null polygons becomes quite a simple exercise once you have these twisters. And in fact, typically what you do is you write the only thing that makes sense and it's always correct. Okay, let me see what else do I want to say. This I can skip. So now finally, as we said, these guys have no cross ratios, so things start to becoming very interesting as soon as we go to 6 points. So let's go to 6 points. Okay. And now we have some twisters, Z1 up to Z1, Z2, ... up to Z6. Okay. And now let's see how can we generate a family of hexagons. Okay. Now we do want a family of hexagons. So let me tell you how we do it. We do the following. We take this cusp and draw a line that is null separated and that hits this point. So this is a null line, and now we know how to fix these lines and how to understand where the points are, where they hit. We take this cusp and do the same here. And now we see that the hexagon is a sequence of 3 squares. The first one here, the second one, and the third one. Right? Now the hexagon is a sequence of 3 squares. Okay? 3 null squares. This square number 2 has 4 twisters and it has some symmetries. Sigma, tau, and phi. These are the symmetries of this middle square. Okay? And now what we do is the following. We start with some random twisters, some random numerical twisters. A bunch of 1s and 0s, or if you have lots of imagination, you can put some 2s and 3s and 5s and so on in your components. So you start with some random twisters, like I did for the pentagon there. And then you act with the symmetries of the so-called middle square, which is the square number 2, on the bottom twisters, in this case Z1 and Z6. Okay. So let's see what this gives. Let me give you an example of what could be the outcome of this. So this could lead to something like Z1 equal. So if we act with the symmetries, you see the matrix. Where is the matrix which contains the symmetries of the square? It's probably behind here, right? No, it's behind here. It acts with the symmetries of this square. So let me write Z1, and you will see that indeed it came from acting with this matrix on something. E to the sigma minus I phi over 2, 0, for example, e to the tau plus I phi over 2 e to the minus tau plus I phi over 2. So you see this comes from acting on the twister, random twister 1, 0, 1, 1 with this transformation. Then Z2, well, Z2, we started random and we keep it random. For example, it could be 1, 0, 0, 0. This would be the same twister as the right twister that we had there. So this could be the right twister that we had there. Okay? And just because I want to tell you an exercise, I will write all twisters, because I will tell you something for you to do. Sorry? Z4 has too many things, that's true. Thank you. Okay, so Z6 became alone here. Okay. So let me now explain what is the geometrical meaning of these operations, why we are doing this, and why this is the correct thing to do. Okay. Or a useful thing to do. But any question about what we did? So it might not be clear why, but is it clear what we did? It's not possible to divide an hexagon into two squares. Two squares? You want to unite the cusp, opposite cusps? Yeah, yeah. Opposite cusps, this would not be a null line. Right? So what Pedro is proposing is to unite this point with that point up there, but that's not a null line. These points are not null separated. You see, here we are building it into smaller polygons, but in the same family, null polygons. So then all these squares that we are breaking them into, they are all null squares. But since you ask, let me tell you, so what is special, what corresponds, what's the physical meaning of these 2 points becoming null separated? So think about it while I erase. So suppose we have a scattering amplitude, so each amplitude is a polygon, right? So each kinematics of the amplitude is one shape of the polygon. What is happening when 2 opposing cusps are becoming null separated? So this cusp is becoming null separated from this one here. Someone can venture? Try. What? Non-connected? Exactly. Yeah, I think it's probably. I think if I translate what you said, I think that what you are saying is that some set of momenta are becoming null, right? So what is happening when these 2 points you see, this point becomes null separated from this point, it means that this vector plus this vector plus this vector is a null vector. Right? So this point becomes null separated from these points become null separated. Null separated when k, I don't know, let's say k1, k2, k3, when k1 plus k2 plus k3 square is going to 0. So these are exactly these factorization points that Freddy was discussing. So then an interesting question that we want to ask, once we will have this expression for the Wilson loops, is exactly that. What happens as I take my Wilson loop solution that we will have and start putting cusps to be null separated? Do we get poles like the poles that Freddy was using, or do we get them but only at weak coupling? What exactly is the physics when this kind of degeneration happens? Okay. So let me first, let's now see what happened here. So now our hexagon depends on 3 parameters, sigma, tau, and phi. Right? So we have a 3-parameter family of hexagons. And this is exactly what we needed. We said we want to find 3 cross ratios, like 3n minus 15 when n is 6 is 3. So concerning counting, it's good. We generated a family with 3 parameters, and that's exactly what we need to describe an hexagon. Okay? But it's more than just a question of counting. This, of course, we are choosing these variables already anticipating some dynamics that are to come. Now let me explain that part. So what we are doing here is the following. We are thinking that we have our hexagon. Okay? And suppose I take this square, okay? And I want to see what is flowing in this square. So I will want to say separate this square by a plane, this idea of putting some surfaces like David was doing, and ask what is flowing here from bottom to top. Now, what's the difference with respect to the usual surface that David was doing, which were encircling operators? There we had the vacuum. But here, when these surfaces, there are already a quark and antiquark piercing this surface, right from the get-go, right from the beginning. So what is happening is that between this quark and antiquark, there will be some flux tube between the two. Okay? And this flux tube is propagating in this square, and this square has symmetries. So the states of the flux tube will transform according to these symmetries. Whenever you have a symmetry, your states transform in representations of this symmetry. So what will happen is that these states that you sum over, they contain, say, excitations of your flux tube. And these excitations have quantum numbers associated to the symmetries of this square where they are propagating. So this Wilson loop will be given by a sum over all possible states that can flow when I cut it into 2. Some probability amplitude for creating them, and then there would be e to the minus tau times the energy of these states plus I momentum of these states times sigma plus I angular momentum of these states times phi. Okay? So if I choose these variables and then take my amplitude, take my Wilson loop and expand it, I associate a physical meaning to whatever multiplies some symmetry, which is a time translation, it's an energy. What multiplies a space translation is a momentum. What multiplies an angle is an angular momentum. Okay? So this will be quite convenient once we will understand this Wilson loop precisely from this point of view. I'm just jumping ahead, just motivating why I'm doing this. And what do we do once we want to study things flowing from a region A to a region B in the presence of some symmetry, like spherical symmetry or dilatations, for example? So let's think of dilatations. What do we do when we do the usual OP? We take 2 points and 2 other points, and we make OP of these 2 points, and you study states that flow from these 2 points to these other 2 points. Right? This is what we were seeing all over in these lectures of David, right? We take OP of these 2 points, sum over states that go to these 2 points. Now let's use the same words that I'm using there. I'm saying first start with some random points. For example, 0, 1/2, 1, infinity. Okay, this is general points. Now act with dilatations on 2 of them. So you transform 0, 1/2 to 0 and 1/2 times z. And now you expand in z. And when you expand in z, you know that powers of z, because z is conjugate to dilatations, the powers of z in the exponent, you read the dimensions of the operators. Okay? That's exactly the same. Of course, you don't want to fix 4 points and act with the symmetry on everything. Otherwise, you do nothing. You're just so if you want to see what flows from A to B, you take the group A and act with the symmetries on A. So that's what we are doing. We have, by this decomposition, what we are doing with our polygons is tessellating it, is giving them an order and saying there is the bottom square, the middle square, the top square, and we will study things with a quantization. We are using these kind of words in this school where we use different planes to quantize in different ways. And here we quantize from the bottom of the polygon till the top, and we want variables to describe this quantization, and therefore what we want to do is act with the symmetries of the middle square and act with those symmetries to the bottom of it. Okay? Let me try to make it even more explicit, and let's for that compute what are the cross ratios with these twisters. Okay? So first, as an exercise, is what I wanted to say. Now with this exercise, just to see what these twisters are, let me put here as exercise. Compute Z, the middle twister 1, and Z, middle twister 2. You see there are two lines there. So compute these guys. Okay? So the answer, I'll tell you, but the answer is to find, is that these guys are the same as our first square. Okay, so you see that Z2 and Z5 are already the same. Z5 is here and Z2 is here, is already the same as Z left and Z right of the first square. Right? So I'm saying that Z middle 1 and Z middle 2 are the same as Z bottom and Z top of that square. Okay? This is the first part of the exercise. And the second part of the exercise is then construct, which is trivial after what I just said, construct the matrix that preserves the symmetries of that square and check that indeed those twisters can be thought of as the action of that matrix on some numerical twisters. Okay? And check Z1 and Z6. Okay? Of course, if you believe the first point, then it's true, because for those simple twisters, the matrix is just diagonal. Right? Is it clear? But in general, the procedure is, I mean, it's a bit technically more complicated, but conceptually it's exactly the same. Suppose you started with some other random numerical twisters. Now you compute Z middle 1, Z middle 2, and you get some ugly twisters. Now you have 4 twisters in the middle. 2 are very nice, because you chose them to be very nice, Z2 and Z5. But now Z middle 1 and Z middle 2 are disgusting. Okay, they are just ugly twisters. 0, 1, 7, 5, one of them. They are just ugly. Doesn't matter. Now that matrix has 4 symmetries, which is just, how can I find it? I first transform this matrix into the diagonal matrix, and then I have those symmetries there. So it is just those symmetries conjugated by whatever I need to diagonalize that matrix that I get. And then with that matrix, I act with the bottom of it. Is it clear? Is it clear? Given 4 twisters, I can find the matrix that preserves those 4 twisters, right? Very good. So now let's construct the cross ratios. Let's try to get some further geometrical intuition. We already have some intuition for what tau, sigma, and phi is. Let's see if what we have is backed up by that. So let's construct a cross ratio. Let me call it U2, the second cross ratio. And the second cross ratio, I will define the first and the third in a minute. It's x1 minus x5 square, x2 minus x4 square, x1 minus x4 square, x2 minus x5 square. By the way, it's a very instructive exercise. You see that here we could construct this cross ratio, and it is this distance times this distance over this distance times this distance. Right? And you can do it. All these distances, they are not non-zero. But if the polygon is, for example, a square, how many distances you have that are non-zero? Only the diagonals. So you just have 2 distances. You don't have enough to build a cross ratio. And for a pentagon, you can also convince yourself that you don't have enough distances to build a cross ratio. This is the first one that you have enough distances. So this is another way of seeing this counting. So what is this? Again, let me just write the beginning, but I will not finish. So this, for example, it's 1, 2, 5, 6 in terms of these brackets. And there will be some other brackets over some other brackets, some other brackets. Okay, it's clear, right? 1, 2, 5, 6 from this point. If this would be Z1, this would be Z2, and so on. And now I just take the twisters that I wrote there and plug it into these determinants and get some function of tau. And this function of tau is 1 over 1 plus e to the 2 tau. Okay? So I could have defined tau, sigma, and phi by just telling you what the cross ratios look like. But then the geometrical meaning of this action is less clear, and you will not understand the origin of these expressions. But still, let's qualitatively understand what's going on now. What happens as we take tau to infinity? Well, we take tau to infinity, and this cross ratio U2 is going to 0. Right? What does it mean that U2 is going to 0? Sorry? So what you are saying is that x1 goes to x5. So what one proposal is the following. What your colleague is saying is that 1 and 5 are becoming null separated. So this is becoming a very thin bump. Or, for example, the top could become almost separated, right? It doesn't need to be 1 and 5. It could be 2 and 4 that are becoming almost null separated. So as tau is going to infinity, see what's happening? We are flattening this top and bottom. Okay? But this is not a conformal invariant statement. This is just one way of making u2 goes to 0. But there are other ways. Another way, which is different, is making it very long, is making the denominator go to 0. Let's make x1 4 very big. It also works. That would correspond to having a very thin polygon, very thin, and then the top is not flattened at all. It's whatever it wants to be. But this is very thin. This is when, etc. Or we can do a mixture and so on. So there are several ones, etc. Okay? What's important is that in all cases, what we have is a square, because we are losing the structure, either because we are flattening or because we are stretching a lot and we just see a long square, plus fluctuations around this square, plus some small perturbations. And how do I think about perturbations of a polygon? For example, if I flatten and put some small bump on top of a polygon, that corresponds to adding impurities on my Wilson loop, as we said in the beginning, right? As we said yesterday, if we have a Wilson loop and put some small bump, that's like putting some extra fields there. So what we have in all cases, the more conformal invariant way of saying, is that we have some square to leading order. We just stretch it completely, we flatten, we get rid of it. Plus, we can have some excitations being produced that propagate. Plus, we can have more excitations that are being produced and that are propagating, eventually interacting with each other and so on. Plus, dot, dot, dot. And this would come with, say, e to the minus tau. This would come with some e to the minus 2 tau. This is schematic, of course. We'll make it precise in a minute, but this is kind of the idea of what you expect. And you see, this picture is nothing but this picture here, where we are starting to flatten, and we will get to leading order. We flatten completely, we get just the vacuum. In other words, we stretch such huge polygon that only the vacuum can propagate from bottom to top. But then we start getting corrections. Then the first excited state, second excited state, third excited state, and so on. Okay? So I gave you one cross ratio only. There is U1, which is just, or let me write first U3. U3 is just U2 when I rotate cyclically my points. Xi goes to xi plus 1. And U1 is U2 when I rotate my points. Xi goes to xi minus 1. And I can also compute them. They are not as simple as that one, but let me just write for completeness, such that tomorrow we can use it. E to the 2 sigma plus 2 e to the sigma minus tau cosine phi plus e to the minus 2 tau. You see, this is nothing fancy. It is just taking the twistors we wrote and plugging them into a bunch of determinants. And U1 is just e to the 2 sigma plus 2 tau times U1 times U2 times U3 times U2. Okay. So in other words, we have this family of polygons where, roughly speaking, what is happening is that tau corresponds to flattening this polygon. Sigma corresponds to moving this cusp left and right, so moving where this cusp is. And as we are flattening, phi is related to things orthogonal to this square. So if you want where this cusp is orthogonal to this plane. Okay? So once we flatten, after flattening, we still have the freedom of moving where this excitation is. This is sigma. Okay. Any question? So let me erase some more. And we will conclude now with the geometry. Yes?
There is a limit to get the pentagon.
Sorry?
So there you get the square, but there is a limit to get the
No. If you don't put insertions, you don't have a way of distinguishing. You are just removing cross ratios and no. Tomorrow we will see how we get the pentagon, but it's not. At least I don't know how to get it from an hexagon in this way. Very good. So now, we did squares, pentagons, hexagons. Now let me summarize by just doing any general n-gon, because it's not more complicated. Now that we understood, the complexity stopped now. Okay? And I will anticipate what will be the use of the pentagons, because so far you see the squares were nice. The squares were the middle part where things propagate, and we were using the symmetries of the square to parameterize the geometry. So if you want, squares are what are putting together these polygons and giving us the geometrical picture of how things are stretched, not stretched, where are the cusps, and so on. And as I will explain now, pentagons are related to how do we jump from one square to the next square, which is perhaps not surprising. We emphasized as soon as we wrote a pentagon that the pentagon can be thought of as the union of two squares. That's why we were computing this middle stuff. Okay. So what about a general polygon? So let me maybe do an heptagon, because the heptagon is general enough that you'll see the full structure. Okay? Let's see an heptagon here. Now the idea is the same. We break it into squares, into a sequence of squares. So we start with this cusp, draw an O line that intersects somewhere here. We take this other cusp, we alternate, and we hit it here. Then we take this one, we draw an O line, and we take it here. And in this way, we have a sequence of squares. Now instead of 3, we have 4 squares. Okay? And now what we do is we focus on the middle ones. Okay? So again, let's see the recipe. First step, we generate some random Z1 up to Z7. Second, we find the squares. So we compute all these middle twisters. So we compute all this Z middle. Okay? Clear? Now, for each middle square, so we construct the middle square, the symmetries of the first middle square that depend on sigma 1, tau 1, and phi 1. This is this first square, sigma 1, tau 1, and phi 1. You construct it once you know these 4 twisters of the square. And then you construct the symmetries of the second square, sigma 2, tau 2, and phi 2, once you know these 4 twisters here. So we construct this matrix and the symmetry of the second square, sigma 2, tau 2, and phi 2. Right? And then we act with M1 on the twister Zi to the below M1, below the square 1, and we act with the twisters M2 on the Zi below the square 2. And now these twisters now depend on all these sigmas, taus, and phis, and they generate a family of 6 parameters. So you see this twister here, for example. This twister here is acted upon by M1 and M2 because it's to the bottom of both squares. Right? Whereas this one, for example, would be acted by M2 only. It's to the bottom of M2, but it's not to the bottom of M1. In this way, whatever this Wilson loop gives, once I expand it at large tau 1 and tau 2, what will appear multiplying tau 1 will propagate in this square, and what will appear multiplying tau 2 will be propagating in this square. Because for tau 2, I measure its energy of everything to the bottom of it, and for tau 1, everything to the bottom of it. Is it clear? And now you generalize. If you have more polygons, you just put more tau I, sigma I, and phi I. So in general, the general picture is that we have a Wilson loop that depends on sigma I, tau I, and phi I, and on the 't Hooft coupling. And how many I runs from where to where? So we have two examples. Hexagon is 1, and heptagon is 2. So can you get the general formula? From 1 to n minus 3 for the hexagon doesn't give 1. N minus 5. Right? For the hexagon, 6 gives 1. N minus 5. And how much is 3 times n minus 5? Is 3n minus 15. Okay? Which is the good number of cross ratios that we need to parameterize a polygon of n edges, as we saw in the beginning. Okay, great. So let me summarize what will be the picture that we will have in the end, and let me make an analogy with what we have for correlation functions, since we had all these lectures on correlation functions. And here we have null Wilson loops. Okay? Yes? So once you specify all the geometry, you specify the contour. Right? So this gives you the contour. Now at the end of this point 4, we have a contour, which is a polygon that depends on sigma 1, tau 1, phi 1, sigma 2, phi 2, tau 2. This gives you just a contour. Now you need to compute the expectation value of the path order exponential going along that contour. For example, at one loop, it's what we saw yesterday. We pick a gluon at the point of this polygon going to another point of the polygon. This is what one loop. At two loops, the gluons start interacting in the middle. At strong coupling, it's a minimal area that ends on this shape at the boundary of ADS. Right? But that's a complicated problem. So today we do kinematics. That's dynamics. Now, but let's conclude with an analogy with the kinematics with correlation functions. So here, when we have, let's do, say, the heptagon. And let me tell you that the heptagon, I'm jumping the hexagon, will be the analog of a 5-point correlation function. Of course, the hexagon is 4 points, but you will be clear. From this example, you can reduce to the hexagon trivially. This is a bit more general, and it's instructive to start with this. What would we do here with a 5-point function? Let's start. So we take 2 points, and we do an OPE, and we sum over all states generated from the OPE of our 2 external operators. Then we take an OPE of that state with another operator, and then we close, and here we sum over psi2. You agree? Here I use the OPE twice. First operator, then a third time. And what do I do here? I sum over the states psi1 and psi2, and then I have some e to the minus tau times psi1 minus tau prime times psi2 times a product of 3 structure constants. Right? One here, one here, one here. Right? You just did 4 points. For 4 points, you just have one sum, and e to the minus tau is z bar. Is it clear? But this is the general structure. You see, if you put more endpoint functions, you have psi1, psi2, psi3, and so on. Now let's see the analogy here. Here also we are saying we have some flux tube state, psi1 on this square. This is psi1, it's probably too small. And here I have psi2 on this second square, some other flux tube state on this square. Right? Do you agree? And what are we saying that we do here? We sum over the states in the first square and the states in the second square, e to the minus tau 1 times energy of the state in the first square, minus tau 2 times energy of the state in the second square. And you remember, in a CFT, the geometry is here, and then the structure constants don't know about geometry anymore. The geometry is taken care by the propagation part. It's z bar factors. And then the structure constants don't depend on geometry anymore. Similarly here, the geometry part is in this propagation. It propagates here and it propagates here. What is the analog of the 3-point function here? Right? That's the question then. What's the analog of the structure constant of this C? We had 3 C's here. So what are these C's? This C is the C. This is one C. This is another C. This is another C. So it's what governs the transition between this psi1 and this psi2. So what is happening here? What's happening here is that, you see, let's see what governs the transition between psi1 to psi2. We have 2 squares, and what happens when we join 2 squares? What picture do we get if I join these 2 squares? A pentagon. And what picture do I get if I join the first 2 that I can draw like this? I get another pentagon here and another pentagon here. Right? So what we will have here in this picture is that we will have this propagation part times a pentagon that translates from the vacuum state in the minus infinity of this square where I put nothing. So it goes from the vacuum. And then on the next square of this pentagon, I have the state psi1. And there is some probability amplitude of going from the vacuum to psi1. And then there will be some pentagon from going from psi1 to psi2. And then some pentagon from going to psi2 to the vacuum. Right? You agree? So these pentagons, this pentagon is exactly the analog of the structure constant, and this geometry part and the symmetry is conjugated to this geometry is exactly the analog of the dimensions and the spin of local operators. Now the operators will also have some energy and some momentum. Okay? And these structure constants here, these C's, don't depend on geometry. They are just numbers. They are just structure constants, right? Why they are not numbers and they don't depend on the geometry? Because with 3 points, it doesn't matter how I draw the 3 points. They are all conformally equivalent. Pentagons the same. If I draw a pentagon, pentagons don't have cross ratios. So this is just a property of pentagons. If I ask, what's the pentagon transition between a state in the bottom square to the top square? I don't need to specify is the pentagon convex, concave, and so on. This is just a way of drawing, but they are all equivalent. So there's no geometry in them. So we managed to isolate the geometry that will come now from these exponentials of the energies and momentum and so on of the states, and the transitions between the polygon. So we are breaking down our complicated problem into smaller building blocks, squares where things propagate, and pentagons that join different squares. Exactly like in a CFT, we use dimensions to propagate the states and structure constants to fuse them and to allow them to interact with other states and propagate along a chain of an endpoint function. Very good. So I think it's good. It's a good point to stop. So tomorrow we will start by fixing a small imprecision. This is not totally correct, because this is assuming life is perfect and there would be no divergences, no infinities to get rid of, and so on. So tomorrow we start by regularizing this, by saying what exactly this object is. It's not just the path order exponential, because that object would have divergences. We have to regulate a little bit to make sure we get rid of those divergences. Once we do, then we will start understanding how exactly do we compute this object here. And we are starting to go now in the direction of exactly the question, given the loop, how do I compute it? And in particular, how do I compute it beyond weak coupling, but at any finite coupling? Okay? But the variables are extremely important. Once you have the right variables, it's important for several reasons. It's important for you to conjecture what the physical picture is, but also to analyze data. If you go and take Wilson loops that other people computed using, say, BCFW or other tools and so on, and you start writing them in the right variables, you start seeing the structure. You start looking at the objects and recognizing the energies of states, the pentagon transitions, and so on. So it's very important to have the right variables. Also to analyze data that is written in normally other variables and to highlight the physics that normally is hidden there. Very good. So I think it's enough for kinematics. Thank you. Questions?
in saying this, you're not much about invariance in testing. So as far as I know, it's state. I feel like that some converges.
So in the CFT, there are two things. There is the thing that the OP converges and that there is an overlapping region of convergence. That still holds here, because that you can analyze by seeing when are the first singularities of your tessellation. That's related to asking, here in a 4-point function, we need these 2 points to be closer to each other than these 2 points are, right, if we want this to converge. Then when we go to conformal blocks, it's even better, and that is amazing, it converges everywhere. So this we don't have here because we will not have conformal blocks here. But the first version of convergence, where it converges in a finite region, we have. So this is related to the question, we pick the particular order to choose our tessellation. What about choosing another order? Like in the OP, we do OP in one channel, what about doing in another channel? So on, we could have chosen different orders. And indeed, if I do a polygon very stretched like this, I want to tessellate like this, and there will be some finite radius of convergence where this will converge. And then if I want very, very different shaped polygons, I have to analytically continue starting from those. So understanding these questions like channel duality, different tessellations, and whether you can use two tessellations that have some convergence radius of that converge in some radius and so on, I think it's true, but it's not something that we cleaned up. So I think the statement is it converges in the same sense as it converges in a CFT before you sum over conformal blocks, before you translate to conformal blocks. Because the conformal symmetry is spontaneously broken by the presence of the flux field. So, yeah. So you can ask, are the states, so you compute these energies of your flux tube, right? And you ask, do you have a notion of descendants? Is the spectrum of states organized like you have some state and some state with energy, which is 1 unit more, 2 units more, 3 units more? And it's actually very fun if you go to weak coupling and you start taking amplitudes that people computed using any method, and you take these objects, you write them first in these nice variables, now we understand how to do it, and then you expand at large tau. You stretch, you expand, and by expanding you read the energies. And you see that at weak coupling, beautifully it works. There is some structure of some Vieira structure where the states are separated by 1, some SL2 structure, and they are just separated by 1. And then you see that it breaks down at 3 loops. At 3 loops, there starts to be a splitting of the spectrum, and this is spontaneously broken. Yes?
So I'm a little bit confused about this expansion there with the squares.
Yes.
It seems that it's an expansion in tau, right?
In large tau.
But you know.
Again, it's important to distinguish kinematics from dynamics. One thing is to know how the cross ratios are parameterized in terms of tau. That's fine. So you see, typically people don't use these variables tau, sigma, and phi. It's a bit crazy to use these variables. Why not say that the hexagon is a function of u1, u2, u3, where u1, u2, u3 are the 3 cross ratios? It's a bit like saying for 4-point functions, why don't we use u and v? Why do we use this variable rho that David at some point started to introduce? Because rho was better. Rho was conjugate to this translation in time. Rho was the right variable. But there was some price to pay. For example, rho was very unfriendly to changing channel, right? In the sense that changing rho was very natural from one channel. From the other channel, it's not so natural. Like z goes to 1 minus z. It's natural for one channel. For the other channel, it's something a bit unnatural. Here also, these variables, they are perfect for a given tessellation, but they are awful for describing, for example, making manifest cyclicity of this object. If I have an hexagon, I can cyclically rotate and I get an hexagon again. And this is totally obscured by this convention. But what we are doing here is we first go to this variable, tau, sigma, and phi. Now I don't speak about cross ratios. I mean, there's no cross ratio. There is sigma, tau, and phi. Then what I'm telling you is that what we will see is that we will consider this object by expanding it at large tau and writing an infinite series. And we will be able to write all the terms. So in principle, we can resum it back if we want. And this expansion at large tau is the analog of saying that suppose I give you a 4-point function and I give you the expansion at small z bar, which is the OP expansion, right? And it's very good. It's what David showed. It converges super well. So if I give you the first 20 terms, you can probably get already like 10 digits or something at any finite coupling. So for all practical purposes, it's the idea that in physics, you keep the lowest energy states, and the physics, you don't care about what happens at the Planck scale. More questions? Again, this is just kinematics, right? So just we are just preparing ourselves to do the serious computation tomorrow. Very good. Thank you. And Sherman. 5 to 4. 5 to 4. It's very generous. Okay, that's fine. Okay, we are 10 minutes late. That's good.
I've got a slightly sort of tricky question. So when you're going to twistor spaces, you're using the essentially SO6 list.
SO2,
yeah, so that's so yeah, well, yeah, that's the question is about what real form you're using. So SO24 has is that the same real form as SL4? So for example, when you wrote down the matrix that fixes with your symmetries, this wasn't real. This wasn't SL4R Is that just is it SL4 or is it something real?
It's what I wrote. And if you have some names for it, I don't know. Probably SL4.